Hello and welcome back to Calculus 1. We are starting chapter 5 that will explain some very basic ideas about integration. We are also going to learn the most important integration technique called U sub, all the way at the end at 5.5. Now the first section is approximating area under the curve, and for that we'll need to know that the area of a rectangle, let's say AB, area is given as A times B. Now our rectangles will look something like this. They will be tall and skinny. One dimension will be called delta x and the other would be called f of xn. So, but it's still the same idea. Area is delta x times f of xn, but it's the same, right? So this is what we have as the intro. So let's go and talk about area. You know the formulas for area. You know that area of the circle is, area of the triangle is, area of the trapezoid. Hopefully you also know parallelogram and so on. So now the question is not what's happening with these shapes that you know. What is happening if I want to find area underneath some curve, let's say f of x, right? In this case, that looks like a square root of x right there. So what should I do? Well, we have to build up to the exact. So what I'm going to do is I'm going to break the area underneath into these strips. And let's say I do that at 1, 2, 3, and 4 because I want to know the area on interval 0 to 4. Let's say that's my goal. So the best I can do at the moment is to create these rectangles. They don't look like rectangles yet because the top is curved, but we're going to fix that by using either red or blue rectangles. You see, red rectangles are going to start on the left and create rectangles. And clearly, areas that you are going to get with these rectangles are going to undershoot the actual area because everywhere where I put the red X, that would be an error, because none of that stuff is included in the area of the rectangle, but it is included in the area of the function. So x is the error, and we see there's a lot of it. Now, the blue one would take rectangles on the other side from the right, and it too would create errors. So no matter which one I use, it's going to be off, right? But one is going to overshoot, one is going to undershoot, and that is going to be like bounds for error in some sense. I mean bound for area. So now let's talk about left approximation. It is called the left approximation because each rectangle is using the left point. Now that left point will coincide with some x to the n on the x-axis. So this left point on top will have xn, comma, f of xn as the coordinates. I also said earlier that each one of these lengths over here is going to be called delta x. And that's simple in this case: 1 minus 0, 2 minus 1, 3 minus 2, 4 minus 3, which is always 1 in our case. We'll get the formula for that as well. So if I'm talking about the left approximation, what I have is area is approximated by I have four different areas to worry about. First one is delta x times f at 0, because my left rectangle has 0 as the x input, plus delta x times f at 1, plus delta x times f at 2, plus delta x times f at 3. So I have 4 rectangles and just 4 calculations of length times width. So in my case, this is equal to 1 times square root of 0 plus 1 times square root of 1, because my function is root x and my values at which I'm computing are given by the picture. So what I have here is 1 times root 0, 1 times root 1, 1 times root 2, 1 times root 3. Because the left points, you see that I drew the rectangle emerging from 1, and then I went to 2. Then emerging at 2 went towards 3. Emerging at 3 go towards 4. So those are the left sides of each integral, and the left sides are going to fall on these numbers because they have a rectangle to their right. So what I have is 0 plus 1 plus root 2 plus root 3. Since we are approximating, this is 1 plus 1.4 plus 1.7 to give us 4.1. Now, area is approximated to be 4.1. We know that the actual area is larger because all of my red rectangles were undershooting, right? So all of these red x's are error. So the true area is actually larger than 4.1. But now for blue, with the right hand approximation, we are using rectangles that have their x to the n on the right hand side, and that's also going to be the point where you have your f of xn calculated for the height. So area is approximated by, again, delta x, but now the first one I am working with is f of 1. If you look at your partition here, the right rectangles are at 1, 2, 3, and 4, because you go at 4, which is the right point, and then you draw a rectangle to the left so that the 4 can be the right. So all of my numbers are now shifted by 1. I have delta x times f at 2 plus delta x times f at 3 plus delta x times f at 4. And this is going to be 1 times square root of 1 plus 1 times square root of 2 plus 1 times square root of 3. So whatever your function is, that's what you're going to use. 1 plus root 2 plus root 3 plus 2, which is 3 plus 1.4 plus 1.7. And this is 6.1. So area is approximated to 6.1. And we know that the true area is somewhere in between 4.1 and 6.1. I just hope that this makes sense. You are chopping up the shape into these rectangles. And the rectangle, you either draw the rectangle, right, for a chosen strip. You either draw the rectangle from the left for the left approximations, or from the right for the right approximations. They're both going to be wrong. Some are wrong than others, more wrong than others, right? But now some people said, well, can you just take the average and get the exact? No. If you take the average of 4.1 and 6.1, you're going to get 5.1, and that's still going to be approximation. Now, there is a way to calculate exact value, but we have to build up to that. So now we learned how to do the left and right approximations, and now it's time for us to write a very important sentence. Approximation gets better as we increase the number of rectangles we use. So, but guys, there's never a free lunch, right? You increase the number of rectangles to have better approximation, but you also increase the amount of calculations that you have to do. So, is 10,000 rectangles going to give you better result than 4? Yeah, much better result. But you have 10,000 calculations, right? And on the other one you have 4, plus to add them. Over here you have 10,000 areas to compute and then add them. So you see that there is a trade-off between there's a trade-off between these two things. So now I want to talk a little bit about these partitions, which involve delta x, right? So let interval be, let's say, 0 to 6 with n equals to 5. So this means that my partitions start at 0, and then after 5, 1, 2, 3, 4, 5. So now I have 5 rectangles. So rectangles will be in this. This is just partitioning. What is each of my delta x's now in order for me to get from 0 to 6? Are they whole numbers? No, they're not, right? If I had 6 rectangles on 0 to 6, yeah, sure. Then you go 1, 2, 3, 4, 5. So now there is a formula to compute this delta x, which should be obvious. B minus A over n. So if I use that formula, delta x is 6 minus 0 over 5, which is 6/5. So that's what these are. 6/5 plus another 6/5 is 12/5, plus another is 18/5, plus another is 24/5, and then 24 plus 6 is 30/5. And 30 divided by 5 is 6, and it falls in, right? That's your checkpoint. So if you did this calculation right, you will know, because you keep adding the delta x, and you go all the way to B. So you start at A, and you go all the way through. Do we have to start at 0? No, we can start anywhere. It doesn't matter. This calculation won't mind. So let interval be from, let's say, -2 to positive 5 with n equals to, let's say, 6 rectangles. You know that your first number is -2. That's always your A. And then 6 of these guys. 2, 3, 4, 5. And you know it must end at 5. Otherwise, you are wrong, right? So delta x is equal to B minus A divided by 6 rectangles. So delta x is 7 over 6. So now -2 minus 7 over 6 is negative 6 is negative 7 over 6. That's a whole, it's 1/6, so -5 over 6. Then you add 7, you get 2 over 6. Then you add 7, you get 9 over 6. Then you add 7, you get 16 over 6. And then you add 7, you get 23 over 6. And then when you add another 7, you get 30 over 6, which is a 5. Now you can cancel this to 1/3 and you can cancel to 8/3, but so each one of these is delta x. So you are able to partition over anything because you have that delta x formula. You don't have to just look at problems that are going 1, 2, 3, 4, they line up. You can do any of these. Now, clearly, it's going to be annoying because you will be calculating the left sum or the right sum using these fractions. So it's going to be f of, let's say, 9 over 6. And in that case, you guys, right, would have to compute in the function these annoying numbers. But hey, at least you're not doing calculus, right? So, woohoo. So now, I want to point another thing out. That should be. This is your A, and then this one is A plus delta x. And then the next one over here is A plus 2 delta x. And then A plus 3 delta x. And then we'll have the next one to be 4 delta x, and then A plus 5 delta x to get to these. And then finally you have a B. If you pick any one of these, you see that you have exactly the number of delta x's spelled out to you. 1, 2, 3, 4 delta x's, and you get to this location. So now, I have a formula to locate xn. We'll call it xi. I is the counter. As A plus I delta x. So this formula calculates values of xi at all locations which are needed for our calculation. All right, so to recap, we have some kind of a function. We create rectangles underneath that function. These rectangles has x0, x1, x2, x3, let's say x4, where the first one and the last one are a and b. We have a formula delta x as b minus a divided by n to calculate the delta x increment. And then you find all of the locations, xi locations. I, in our case now, is the set 0, 1, 2, 3, and 4 because those are x0 through x4 values. So xi is calculated as a, which is the first input, x0 is the first number from the interval, plus I delta x. Now delta x is brought in from up there, whatever the value is. So you can now calculate each one of the locations. So that's equivalent to taking your a, you add delta x, then that's your new a, add delta x, and so on. So I think that's it for now, for 5.1. And now we're going to jump into 5.2 and take a look at the use of this. So 5.1, just approximate area under the curve using the middle school skills, right? You have rectangles and you just compute them.